Mhm. Hi, everybody. Welcome to the fourth live session on numerical analysis, NPTEL course. Hello, Ravi Shankar. Ravi Shankar has told hello well before we started itself. Very nice. So, how many are there? Just see. Okay. So there are a few people on live session. Nice. Yeah. So welcome you all. I hope the course is going on well. We are at the last week of the course, and we have covered almost all the chapters of our course. Only thing is half of numerical methods on ODE is still remaining. That is going on now. So if you have any questions, you can ask me. Yeah, so Ravi Shankar is having a question in the other part. Uh, let's wait for his question. Okay, so trapezoidal Simpson's one-third error. Okay. Uh, Simpson's one-third, we have covered Simpson's method. There is a Simpson's one-third rule, which we have not done in the class, but I think there is an exercise problem on Simpson's one-third rule. So what is your question, Ravi Shankar? If you can precisely tell us, it will be helpful. Simpson's 3-8. So that is the one-third rule. Okay. So, Ravi Shankar, if you have any specific question on this, you can ask us. If you recall, we have proved the error in trapezoidal rule, but in Simpson's rule, we have not proved the error part. Odd or even number of integers, how to identify. So, are you? No, I don't still understand your question. Or even number of integers. It's not very clear. See, in Simpson's rule, when you go for composite Simpson's rule, you always need to have even number of integers in your partition. So that is because uh, you want two two intervals to be clubbed in one integral, so that the midpoint is also a node point in the Simpson's rule. So that is the rule in the composite Simpson's rule. But as far as the error is concerned, at least in the trapezoidal rule, you don't need any information about whether you have odd number of integers or even number of integers. It goes well. That's not a problem. But when you come to Simpson's method, again, see the error in Simpson's rule is little bit difficult to prove. So that needs some application of the Ginocchi formula. So we have not covered that in our course. But I don't think it needs any information about odd or even number of integers. Only thing is, when you go for the composite Simpson's rule, you need even number of intervals. That is precisely because you need the midpoint of the Simpson's rule formula. Needs the function evaluation at the midpoint of the interval, right? Therefore, when you take integral xi minus 1 to xi plus 1, then xi becomes the midpoint of this interval. Of course, when you are working with equally spaced nodes, you will have xi as the midpoint of the interval. That will help us to implement the Simpson's rule more smoothly. Okay, otherwise you need to know the function value at the midpoint of the interval, which may not be available for you. So the rule is that you have to use only the node points in your quadrature formula. In that way, when you are working with composite Simpson's rule, you have to work with even number of intervals. But I don't understand why we need to know the number of intervals in the error formula. That is, I'm not able to understand what precisely your question is. If you can make your question more clear, then we will try to answer. Log to the base 10 x from 1 to 5 using, we have the Simpson's rule 1 to 5. So if you have interval 1 to 5, you have to see what is the midpoint of the Simpson's rule. The Simpson's rule that we cover is b minus a by 6 into f of a. In this case, it is a is 1, and then you need to know the value of f at the point a plus b by 2, which is 6 by 2, right? So you need to know the function value at 3. And then you have 4 into f of 3 plus f of 5. So that is the formula. So it goes without any problem. Log to the base 10 of 1 plus 4 times log 10 to the base of 3 plus log 10 of 5. So into b minus a by 6 also you have to put. That is nothing but 4 by 6, right? So that is 2 by 3 will come there. Okay, so that's how the integral goes. And if you want the error is you have to differentiate your function log x 4 times, and then you have a formula for error. So that is, you can use that formula. Of course, it will involve unknown point eta. So you have to differentiate it 4 times, and then whatever comes should be returned at some unknown point eta times b minus a to the power of 5 divided by some number 2880 comes, and that is minus of this is the error. So you can compute it. You can also find an upper bound for that. Okay, so in this I don't know where the odd or even number of interval comes into picture here. Yeah, so Newton code formula. See, this is, we have not mentioned this name, Newton code formula, but what we did in the quadrature formula chapter is basically the Newton's code formula. Okay, I have not mentioned the name, but that is what is, see, what we do is, probably I will open that slide and show you. Okay, so in one of the classes, we have actually oh, we have checked. Okay. Yeah, see, this is the exact interval that you want to evaluate, right? What you are doing is you are approximating that interval by approximating the integrand by the polynomial, right? And then taking the integral of that polynomial. That will, when you write the polynomial in the Lagrange form, it takes this form, right? Because f of xi, this is constant. Li's are actually functions of x. Therefore, you finally have, when you take the integral, you will have sigma I equal to 0 to n f of xi integral a to b Li of x dx. Okay, so these are the weights Wi's. That's what we are getting here, weights. So generally, the quadrature formula is of this form. Okay, so f of x naught w naught plus f of x1 w1 and so on plus f of xn comma wn. This form is called the Newton's port formula. Okay, Newton Cotes formula. So there are two approaches here. One is given, first approach is given the nodes x naught, x1 up to xn to find the weights. W naught, W1 and so on till Wn. Okay, so that is one approach. We have used this approach and obtained some quadrature formulas like rectangle rule, right? Trapezoidal and Simpson. Right? You simply have to integrate this polynomial. Okay, all these polynomials, that is Lagrange polynomials, have to be integrated. That is one approach. Another approach is you are also not given the notes. Okay, you are not given the notes, and also you are not given the weights. Okay, both to find the notes as well as the weights. Then that gives you what is called Gaussian rules. So we have covered both. When you go to do this, it's more useful to go for a method which is called the method of undetermined coefficients. Method of undetermined coefficient. Okay, so the method assumes that the quadrature formula, which is generally approximately equal to, that is what we will write. This exact integral is approximately equal to this form. That is the actual situation. But this method of undetermined coefficient assumes that this quadrature formula is exact when the integrand f happens to be a polynomial of degree less than or equal to n. If you are given n plus 1 nodes, then it will assume that the quadrature formula is exact for polynomials of degree less than or equal to n. So you will apply this condition on the monomial basis of the set of all or the space of all polynomials of degree less than or equal to n. And you will have a n plus 1 unknowns which are coming as nodes, and you have n plus 1 equations. In that way, you can generate a quadrature formula. That is the first type of formula. You will get either trapezoidal rule or rectangle rule or any rule in this way, Simpson's rule and so on. Once you fix the nodes and only try to get the weights. Now, if you also make the nodes to be unknown, then you have to assume that the quadrature formula is exact for polynomials if the integrand f happens to be a polynomial of degree less than or equal to 2n plus 1, because you have 2n plus 2 unknowns, right? Because you have all the nodes which are n plus 1 is in number, plus you have the weights which are also n plus 1 in number. Totally you have 2n plus 2 unknowns. And when therefore you have to impose the condition that the quadrature formula is exact for polynomials of degree 2n plus 1. Okay, that gives you a more accurate quadrature formulas called the Gaussian rules. Okay, so this is the idea of how to derive the methods in our class. We have actually uh, obtained the the quadrature rules, like from the first part we have obtained the three quadrature rules including Simpson's method, and then as long as the Gaussian quadrature rule is concerned, we will only give weightage for n equal to 0, which is nothing but the midpoint rule, and n equal to 1, which we derived in the class. We will not go to ask any question from the examination point of view on any other Gaussian rule, like Gaussian rule for n equal to 2, 3, and so on. Okay, so I hope this helps you to have an idea of what is Newton code formulas. We have covered all this, but I have not mentioned the word Newton code. Maybe I missed it at the time of lecturing. I'm sorry for this, but I think it is written in the notes. Okay, you can refer the notes. Okay. Okay. So Kiran, Paul, hi. Good to see you here. Yeah. So this is also a very good question and important question: how to find optimal value of h if f of x equal to cos x. Uh, uh, yeah. Okay. So this is done in the class also, and it is there in the notes also. Um, the optimal H that Kiran is referring is mainly in the context of finite difference methods uh, for approximating derivatives, especially when you have rounding error. You can see that you will have a term which is coming from the arithmetic error part that involves 1 by h to the power of something, depending on what finite difference formula you use. Okay. Therefore, there is a danger that as h tends to 0, your error can blow up. So there is always a optimal h which can be obtained as the minimum of the upper bound of the total error. Okay, so this is the idea. In particular, you have any function, not necessarily only cos. If you have any function, you can actually first write the upper bound for the total error and take that upper bound and find the minimum of that upper bound. Okay, so if you recall, the total bound is nothing but the sum of the mathematical error and the arithmetic error. So you have to find the minimum of that function. Okay, the minimum is precisely the optimal h. We have illustrated it in with an example in the class. I think we have done in the class for f double dash. Let me see. And let me again share the screen and see what we did in the class. And then I will tell you I think it may be the arithmetic error. Oh, so this is arithmetic error in polynomial interpolation. Finite difference, maybe 2 will tell us what is that. Hmm? Yeah. Okay, so in the class, what we did is we have done the same problem, cos f of x equal to cos x, but we try to use the central difference formula for f double dash of pi by 6. Okay. So if you go through this part, which is also there in the class notes, you will get an idea of how to do such problems. In the tutorial, I think we asked, instead of f double dash, we asked f dash of pi by 6. Okay. So more or less it will go in the same way. For instance, all this will go exactly the same. Okay, there is no uh, difference in this because we are anyway using only cos, right? So all these steps will go on. Therefore, you will have the rounding error upper bound uh, the same as what we did in the class for the assignment problem also. But instead of using D2, we are using DH0 of f of x. How that is given? That is given by f of x plus h minus f of x minus h divided by 2h. This is the formula. Whereas uh, D2H formula is something, if you recall, what is D2H formula? It is given by f of x minus h minus 2 f of x plus f of x plus h. Am I right? Divided by h square. Okay. Now you have this formula. So what you do first is write the dh dash, okay, dh dash not f. Okay, so this is nothing but f, say let's call this as f1 and we call this as f2 after having some rounding error. Okay, so you did some rounding error and found the value of these functions, say denoted by f1 and f2 respectively. Then you have f2 minus f1 divided by 2h. Okay, so when you go to subtract these two, you will have epsilon 2 minus epsilon 1 divided by 2h is the arithmetic error. Okay. Now you have to take the upper bound for that. Okay. So this step, which is for D2, in our case, in the tutorial problem, how that will look like. F dash of x1. X1 is pi by 3 or pi by 6. I don't know what we asked in the assignment. Whatever we asked for, you put that, minus dh bar 0 now, f of x1. That will be, how will it look like? This is nothing but this is less than or equal to mathematical error plus arithmetic error, right? Mathematical error for the central difference formula of f dash is we have proved in the class, right? Proved in the class. I think it is something like h square by 6 into mod f double dash of psi, if I'm correct. Let me just check that. Yeah, there are too many formulas. We have no other. Yeah, so it is h square by 6 into f the triple dash. Okay. f triple dash will come. So this is actually uh, h square by 6 into f triple dash of psi. Plus what is this? This is nothing but, if you recall, this is epsilon 1 minus epsilon 2 divided by 2h. That if you take modulus and take the modulus inside, you will have 1 by 2h into mod epsilon 1 plus mod epsilon 2, right? So this is what you will have. Now you see cos. So what is this? F is cos. Therefore, it's any order derivative will be either cos or sine, whatever it is. It can be bounded by 1, or the best is you take the value of this derivative as just at the point whatever we are given, x1. Okay, I don't remember whether it is pi by 3 or pi by 6. Please refer to the assignment problem for exactly what is the value that we have given. So you can take that and put this, replace this by that number. Okay, and what is this epsilons that we have already, right? I think, yeah, we have them. So these are epsilon 1 as well as epsilon 2. Both are this. Of course, if it is 6 digits, I don't know. Again, you have to check the assignment problem, whether it is given 6 significant digits or any other. See, if it is not 6 significant digits, then this number will change. That's all. Okay, 6 means it's 5. So similarly, you can see if it is 7 or 8, what this number comes. You know the definition of significant digit that we defined in our course, right? So you refer to that definition. Accordingly, you will get some number here, and that number, finally that number will be your epsilons. Okay, so when you go to put that, so you can put that and get the get this term. Okay, now you see whatever it is, the first term is going to be h squared by 6 into some constant will come from here, right? So let's call that constant as k1, okay? Plus 1 by 2h, this is coming, plus some constant will come from here, which we will call as e, okay? Because it's coming from epsilon, so I'm just using the letter e here. Now you see, you have h squared by 6k1 plus 1 by 2h to the power into some constant e. Okay. So I should not use the letter e because in the class we have used it to define this function. Let me use some other letter, say c. Okay, 1. Now what you do is you take this. You have to find what is precisely k. That's not a big deal. It's nothing but cos, third derivative of cos evaluated at whatever point we have given here. Okay, that is k1. And this is nothing but 2 times that epsilon we got in the previous slide. Okay, so both these numbers you can get. Okay. Now you define this function as e of h is equal to h squared by 6 into whatever number you get here, you put that, plus 1 by 2h into whatever number you get from here, you put that, and then find the minimum of this function. Okay, so that will be your optimal h, which we generally denote by h star. Okay. So I hope this is now clear for you. If you have any further questions, you can ask me. All right. So how many people? Yeah. So the same idea as what we discussed in the class. Okay. Let me see what is that question given in the. 11th week is over already.
Yes.
So, and I can see it here. Fifth question. Huh? Yeah, 5 by 6. Yeah, 5 by 6 is what we asked for. Okay. That's nice. Okay. Okay. So that's nice. Any other question you have? So we don't have any subjective question of problem 4. Okay, so Kiran is asking for problem 4. Okay. See, this is F double dash. So this is see, if you recall, you can go with the method of undetermined coefficients also, or you can directly go with the polynomial method, interpolating polynomial method. We are asking for undetermined coefficients. Both will give the same answer, doesn't matter. So let me just explain you how to do that. I don't know how to. I have to share, right? First. So x minus 2h, x minus h, and x plus h, and it is 0.05. Huh? So let's remember this. Okay. Let me share the info. Okay. So how to get W0 and plus W1, right? Let me share and give you some hint. I hope you can see the yeah. So I'll come to Ravi's question, but let me finish first. See, the question is you want f double dash or double dash of x. You want it to be approximated by W naught f of x minus 2h plus W1 f of x x or
X.
x
X minus h. Yes. X minus h.
x minus h, is it?
Yes.
X minus h plus W2 f of x. Say, for instance, this is how you want, okay? You want to, what you have to do is take f of x is equal to 1. This is true for any method, okay? It doesn't matter what grid points are given here, okay? Any grid point is given, the method goes like this. See, how many nodes you have? 1, 2, and 3 nodes. Therefore, you have to apply this formula for 3 cases. F of x equal to 1, f of x equal to x, and f of x equal to x square. Okay. So you have 3 unknowns, W0, W1, and W2. Therefore, you need 3 equations that you will generate from these 3 by assuming that f is just a constant polynomial. That will give you 1 equation, right? Say, for instance, on the left-hand side, it is 0. And now you will, the method of undetermined coefficient says that when f happens to be a polynomial of degree less than or equal to 2, this formula gives the exact result. Therefore, you will have equal to W naught plus W1 plus W2, and that is one equation. Similarly, when you put this, you will have F double dash, which is 0 on one side, and this side you have W naught into X minus 2H plus W1 X minus H plus W2 X. Okay, so we have done this exercise in the class for a slightly different notes. Okay, the idea is exactly the same. Only thing is the notes are replaced now by the notes given in the class work. Okay, this will give you 1 on one side, and this side, no, I think it's not 1, right? 2, yes. Okay. And this side you will have W naught X minus 2H square plus W1 X minus H square plus W2 X square. Okay. So certain terms you can use this equation itself. Okay. And you simplify this equation, and using these two equations, you can simplify this equation. Okay. In that way, you have three equations for three unknowns W0, W1, and W2. That is a linear system. You can solve that linear system to get W0, W1, and W2. Once you have the expression for W0, W1, and W2, you just look at what is W, I don't know what is asked, W0 plus W1, right? So that will have some expression, okay, involving H, okay? You have to find that expression. I think that will come from one of this equation itself, it will come, right? So once you have that expression, then you have to put H is equal to 0.05, and that will give you some answer, okay? Some number it will do. So this is what you have to just plug in into your answer, okay? So that's this kind of things we have done with, I think, central difference nodes. So that is X minus H, X and X plus H in the class. The same idea will go. Now you have just different nodes. That's all is the difference. Okay. Otherwise, if you just go through the video, you will know very clearly how to do that. It's also given in the notes. You can see that. Okay. I hope that is clear for you now, right? W0 plus W1, I don't know whether it is W0 plus W1 or W0 plus W2, whatever it is. Once you solve that linear system and get W0, W1, and W2, you simply add. That will give you an expression that involves H. Now you have a value for H equal to 0.05, right? So you just put that value, you will get the answer, okay? Yeah, so thanks, okay. So the importance of pivoting in Gaussian elimination method, okay? So Ravi, it's a, yeah, so it's a very important question also. You see, we have given an example when we were discussing the Gaussian elimination method without pivoting, which we call as naive Gaussian elimination method. Okay. So in naive Gaussian elimination method, what we do is we simply apply the Gaussian elimination idea without worrying about how these coefficients are and so on. Okay. So in that way, there's a very likely that you may encounter a situation where your leading term, which is sitting as the denominator in the multipliers. Okay, so M 2 1, M 2 2 2 1 2 and 2 1 3 and so on. That's what I guess is the notation. In all this, you have some denominator term. A11 will come in the first step. A22 of 2 will come in the second step, and so on. Okay. If these numbers happens to have some arithmetic error, they tend to increase the overall error in the method. Okay, so to avoid that, we do this partial pivoting. Okay, so the partial pivoting mostly, if not always, tries to reduce the rounding error in the Gaussian elimination method. Okay, so that is the main reason for why we go for the modified Gaussian elimination method, where you have this partial pivoting idea. You similarly have full pivoting ideas also. But mostly what happens is, of course, when you go to do find maximum among many numbers, it is going to add more computational time, right? So there is a good trade-off between the reducing the error and reducing the computational time. Therefore, what people generally see is partial pivoting is good enough in most of the situations. Okay. Full pivoting, well, it will certainly improve the accuracy, but when compared to the time taken by the algorithm, it may be okay if you just go for the partial pivot. Okay, so the importance of pivoting is to reduce the arithmetic error involved in the elimination process. That is the final answer for your question. I hope it's clear. If you have any further questions, you can ask me. So, yeah, good. So, you have any other questions? So, we will try to fix one more live session, maybe next Wednesday. You can see if it is okay. Next Wednesday, same time, we will fix one more live session so that you have finished all the syllabus of the course so that you can once for all get all your doubts clear. Uh, in binomial expansion, okay. Okay. Oh, so Newton binomial expansion. At least we have not covered this. I don't know if you can give me more details on what it is. Then just go on. You can you give more specific question on this? Okay. Yeah. So next week, if you have any questions uh, on the last week, also you can include that in the next class. Overall, we have only objective questions from the examination point of view. Um, as you know, in NPTEL, we have three levels of types of questions or three sections of questions. One is uh, there are 10 questions asked from the lecture that we have given and the notes that I have given. Okay, so if you have watched all the lectures and the notes you have studied, you can answer this 10 questions. It's not a problem. So very direct questions we ask. Okay. Therefore, we clear with what we taught in the class and also what we have given in the notes. You'll be clear from the theory. Mostly these are theoretical questions. Okay. Uh, and then there is another section which has assignments. And I think there are 15 questions from the assignments, which are just the repetition of the assignment. So if you have understood all the assignment problems, uh, if you have not done correctly, doesn't matter. But I think if after the assignment submission period is over, we are giving the solutions for them. Okay, so you try to understand them and try to think by yourself some question which are similar to the assignments that we have done. Okay, so that you can practice them. Okay, so there are 15 questions which are just taken from the assignments only. And then there are 25 questions which are of course, covered from the notes and the lectures that we have given and the knowledge that you gained by solving the assignments. We will ask questions within this only, but some are some of them may be not there at all in the assignment or not there explicitly in the notes, but they only demand the knowledge of what we did in the class and assignments. There are 25 such questions. Okay, so all are objective questions. They can be MCQs or MSQs, just like assignment problems. Okay, so I hope if you are thorough with the material that we have given, you will certainly get full mark in our exam. And my best wishes for you all for having a nice exam. Anyway, we will have one more live session before the exam. So if you have any questions, you can ask me now. How many questions from Python? We don't know. Uh, but certainly, it's not very difficult for you. Okay. Uh, so last week also you are not very comfortable with Python, you said. Uh, See, I don't want to tell how many questions. Then you will decide whether to, avoid learning it, right? So we don't want that. Assume that all the questions are in Python. Just assume that and do better. So we also want you to be good in Python programming of numerical methods, right? So, but whatever it is, if you have done some Python codes by yourself, you will very easily answer those questions, very easily. Okay, so that is how the questions are. Okay. So you need not worry about it if you have done all the assignment problems by yourself. And it may be wrong, that doesn't matter. But if you have done by yourself, you will certainly answer those questions. Okay, how many ever it is, it doesn't matter. Yeah. So it is worth the learning Python because you see Python is very popular now. It is also equally becoming popular among scientific computing, among the researchers and scientific computing, when compared to the MATLAB. Okay, so therefore, it is really fun to also learn Python, even if you know MATLAB. And of course, if you know one language, learning the other language is not very difficult, right? Given that it is more or less, as easy as MATLAB, in the sense that there are many mathematical concepts which are inbuilt as codes in Python also. When you take MATLAB, you have many mathematical concepts that are built and kept in MATLAB, right? Similarly, in Python also, there are many subroutines which are ready to use, and therefore it's also like more as friendly as MATLAB, okay, Python, and therefore it is becoming popular among the researchers. Yes, and therefore it's not very. It's worth learning Python. Okay, in today's situation, it's Python is also becoming more popular. Yeah, it's very difficult to memorize all the formulas. This is true. But if you see, if you carefully go through our lectures, we are giving the ideas behind those formulas. And once you know the ideas behind deriving these formulas, you don't need to memorize them. Okay. Say, for instance, Simpson's method. Okay. You take Simpson's method. If you have to memorize it as b minus a by 6 into f of a plus 4 into f of a plus b by 2 plus f of b, if you memorize that and come to the exam, in the exam hall, you may have a doubt whether it is b minus a by 6 or b minus a by 3, or is it 4 times f of a plus b by 2, or is it 2 times f of b plus a plus b by 2. This kind of doubts comes if you memorize that formula. But if you know that I have to use the nodes a plus b by 2 and b, and just build the polynomial interpolation and integrate it, you can just on the rough work quickly get the polynomial, quadratic polynomial, or you just write the Lagrange polynomial, and just in 2 minutes you can just see what it is, right? Therefore, in that way, you just have to remember the ideas behind deriving these formulas, right? Similarly, if you see secant method, it's a formula. If you see, it's so scary. Okay, it's very big formula. But if you know that secant method is just the point of intersection of the secant line with the x-axis, you know what is secant line? It's the line joining the point A, x naught comma f of x naught, x1 comma f of x1. So you know how to write the line joining these 2 points, right? So we know all from our school itself how to write this equation of the line. Just to write the equation of the line equate to 0, you will get the formula. Why you have to remember that? Right? If you see really the secant method formula, very difficult to memorize and remember it. Okay, but you just open your rough work, just in the corner, you write the equation, equate it to 0, you will get what is x2 expression, right? So in that way, if you think you have to memorize, it's very difficult. But if you just remember the ideas behind these methods, which are more or less, we built these ideas as stories. If you see uh, in our lectures, we built these ideas just like, storytelling. Okay, we started with bisection method, very intuitive method. Bisection method is very intuitive. From there, how regular falsy comes. Okay, and from once you understand regular falsy, secant method comes just for free, because there is nothing new in secant method once you understand regular falsy. Once you have secant method, it's a line joining, it's a secant line intersecting x-axis. You just take that 2 points tending to each other, you get the tangent line that becomes the Newton's method, right? So in that way, if you build these stories in every chapter, then you just have to remember the stories, okay? And then you just, if you are not confident with the formula, just quickly derive it and see how it comes, and then use that formula and do the problems, okay? But memorizing is, as you say, I agree, memorizing is very difficult, but you don't need to memorize. That's the final thing, okay? So I hope you will agree with me. I don't know. Huh? Uh, Yeah, very nice. Thanks to Kiran and Ravi, and also to others who attended the live session. You made the live session very interesting today. A lot of discussions we had. Okay, I think it's time up. We have to close the live session now. Thank you very much from me and Shubham. We will meet next week. Okay, and prepare well, and my best wishes for your exams. Thank you very much. Huh? Okay, thank you. Bye. So you can close. Huh?